An historic milestone was completed in May 1966 at Kennedy Space Center, Florida, in the Apollo Saturn V program to land Americans on the moon by the end of this decade. The event started when the first stage of a facilities checkout vehicle arrived by ocean-going barge January 19, 1966. Once inside the vehicle assembly building, this rocket section, measuring 138 feet long and 33 feet in diameter, was lifted into a vertical position by overhead bridge-type cranes. Slowly and gently, the giant of the space age was lowered into place on the platform of a mobile launcher, then secured to 4 hold-down arms that support the entire vehicle during checkout operations. The 82-foot-tall second stage, which arrived at the spaceport March 5th, was moved from its checkout stand in the building and made it to the first stage. This section of the rocket weighs 80,000 pounds empty and over 1 million pounds loaded with fuel. The Apollo astronauts will be injected into Earth orbit by the Saturn V's third stage. This section will place itself, the instrument unit, and the spacecraft into an Earth parking orbit about 100 miles high, the first leg of the moon journey. Like the second stage, it will use liquid hydrogen, which provides 40% more thrust than the conventional kerosene-type fuel. The instrument unit, a huge ring more than 21 feet in diameter, houses the complex electronics which guide and control the rocket during flight. The 3-section payload, including a model Apollo spacecraft similar to those which will later carry men to the moon, was then placed atop the massive space booster. The uppermost section of the Apollo Saturn V, the launch escape system, was fastened to the command module or crew compartment. This emergency unit is designed to pull the Apollo spacecraft and its occupants to safety in the event of booster failure. Completely assembled, the checkout vehicle stands 365 feet high and is an exact duplicate of the actual Saturn V, except that it has no engines. On May 25th, Space Agency officials and more than 500 invited guests attended a short ceremony which preceded the rollout of the Apollo Saturn V. A 3,000-ton transporter lifted the launcher and assembled rocket off its support pedestals and moved through the 456-foot-high doors of the building. Thus began the slow trip to the launch pad more than 3 miles away. The test vehicle, designated the Apollo Saturn 500F, will never make the journey to the moon. It is, however, used to verify launch facilities, train launch crews, and develop test and checkout procedures at the Space Center. The first flight rocket will later make this trip. The transporter moved the Apollo Saturn V slowly toward the pad. The total weight of the rocket, mobile launcher, and transporter is 18 million pounds. This massive load moved over the specially constructed crawlerway at speeds up to 1 mile per hour. The mammoth tracked vehicle, weighing almost 6 million pounds, performed perfectly during the historic test of the new mobile launch concept. 2 diesel-electric generators controlled from within the crawler provided the power to drive the enormous transporter. Halfway to the launch pad, the Apollo Saturn V passed the 402-foot-tall mobile service structure, which is still under construction. When completed, it will be used by technicians to service the mighty rocket at the launch site. The most critical part of the trip was the 5-degree climb to the top of the launch pad. The transporter's hydraulic leveling system was put to a severe test in keeping the mobile launcher and rocket perfectly balanced as it moved up the slope. Upon reaching the top of the launch pad, 48 feet above sea level, the transporter gently lowered the massive cargo onto the pad's support pedestals. Thus, America's space program passed another major milestone as the Apollo Saturn V test vehicle completed its historic move. A 3-mile trip to the launch pad, where man someday will begin his greatest adventure, a journey to the moon.
43, 44, 43.5, 44.
When the 3 astronauts who go to the moon complete their final checklist before launch, they are ready for a 500,000-mile round trip. Their course is pre-planned and precise.
17, 16, 15,
And at their command, They have some of the most sophisticated devices made by man.
5, 4, 3. Ignition detected. Transmitted 5 enter. Clock start 5 enter. Thrust okay.
At liftoff, they are guided automatically until they reach parking orbit around the Earth. A small, complex computer in the Saturn V's instrument unit directs the rocket engines. They, in turn, push the launch vehicle into its proper orbit. But the astronauts are not alone. Their position is constantly being monitored and sent to the flight controllers at Mission Control in Houston. There, computers compare their flight with the one planned and revise the flight data.
Program 12. Trajectory controllers enabled.
The updated information is sent back to the command module, where it is stored in a small computer, the brains of the Apollo guidance and navigation system. This system makes it possible for the astronauts at any point in their lunar mission to pinpoint their position. In Earth orbit, they can use their sextant. An astronaut lines up a known star and a prominent landmark, and feeding his readings into the computer, gets his position back from the machine. As they leave Earth orbit and head for the moon, the astronauts are faced with another guidance problem, that of determining their attitude, or the direction the spacecraft is facing. The astronaut navigator finds a known star in the wide-angle telescope. Using a fingertip control, he changes the attitude of the spacecraft to bring the star into line. Once he has the star in position in the telescope, he moves the optical sextant. He lines the sextant up with the star and makes a reading. He must repeat the process with another known star so that he has two readings to give to the onboard computer. From this information, the computer determines the attitude of the spacecraft. Once the attitude is known, the 8-ball can be aligned. This device, similar to those used in airplanes, is stabilized with gyroscopes and connected directly to the computer. To the astronaut, it's the most important display next to the computer itself. When set, it becomes the primary guidance instrument in the spacecraft and is used to orient the spacecraft for the mid-course maneuvers. This information is vital to their mission, particularly for the mid-course adjustments they will have to make when their engine has to be accurately aimed for firing. To find his position in space, the navigator goes through the same kind of routine he used in orbit around the Earth. He takes a sextant sighting on a known star and on Earth's horizon. The computer, given this information, tells him where he is relative to the Earth. As the spacecraft approaches the moon, the same procedure, this time using the lunar horizon, tells him how close he is and his position in space. The 8-ball and the computer, armed with updated information from tracking facilities on Earth, direct the aiming of the spacecraft engine for retrofire to slow the craft down to orbit speed. The navigator can then determine the altitude of the orbit and the position of the spacecraft, just as he did around Earth, using a star and a lunar landmark in the command module sextant. For the actual landing, the lunar module uses a landing radar system tied into an onboard computer to tell him where he is relative to the actual landing spot. For the liftoff and the subsequent rendezvous, another radar unit feeds the necessary information to the lunar module computer, while the astronauts keep track of the orbiting command module with a sighting device on the window. The trip back to Earth is the opposite of the trip out. Star and moon sightings give the spacecraft's position. Mid-course corrections are made in the same way, using the 8-ball and the computer. The success of the first visit by Americans to the moon depends on many things. The rocket engines must perform without fail. The spacecraft systems must all operate reliably, and the men in flight and on the ground must be dedicated and able. And a major key to this success is the Apollo guidance and navigation system, telling the astronauts where they are and how to get where they want to go.
Six, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
Tranquility, we copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot. At the foot of the ladder, the 11-foot beds are only depressed in the surface about 1 or 2 inches. And step off the limb. That's one small step for man.
Beginning with man's first attempt to fly faster than the speed of sound, the National Aeronautics and Space Administration's Flight Research Center has played an important role in establishing this country's leadership in world aeronautics. The Flight Research Center was established in 1947, when a small group of engineers and technicians were assigned to the X-1 Flight Research Program. Since then, the specially designed and highly instrumented research aircraft has become one of the most valuable tools of advanced aeronautical research. The X-1 was the first research aircraft to fly faster than the speed of sound. Its mission was to probe the sound barrier. Powered by an XLR-11 rocket engine rated at 6,000 pounds of thrust, it used propellants of ethyl alcohol and liquid oxygen. The X-1, air-launched from a B-29 mothership, made its first powered flight in 1946. In 1947, Captain Charles Yeager piloted the X-1 in level flight faster than the speed of sound. The D-558 Skyrocket was the second rocket-powered research aircraft to fly. It was designed to investigate jet aircraft characteristics at transonic speeds, including stability and control and buffet investigations. The D-558 was the first American aircraft to use swept-back wings and stall fences, features that are common to our present-day commercial jet transports. The D-558 was the first aircraft to fly faster than twice the speed of sound. The largest of the early research aircraft was the X-3 Stiletto. It was 69 feet long with a wingspan of 22 feet. The primary mission of the X-3 was thin wing research. Powered by two jet engines, the X-3 had a top speed of slightly in excess of Mach 1, the speed of sound. The X-4 was easily recognizable by its lack of a horizontal tail. The X-5 was the first aircraft that could sweep its wings from 20 degrees to 60 degrees in flight. This variable sweep concept is being used in current fighter and bomber designs. The X-5 made its first flight in 1951. First flown in 1955, the X-1E was used for thin wing research, aerodynamic heating studies, and stability and control investigations. The most successful of the research aircraft was the X-15, which made its first powered flight on September 17, 1959. The three X-15 aircraft flew 199 flights to obtain data on the aerodynamics of hypersonic flight. The X-15 is the only manned aircraft that has flown to altitudes of 354,200 feet and speeds of Mach 6.7. The flight program made significant and unique contributions to future aircraft designs and proved that winged Earth exit and re-entry are well within the control capabilities of man. The XB-70, the world's largest experimental aircraft, was 185 feet long, had a wingspan of 105 feet, and was 30 feet high at the tail. It was capable of flight at speeds of 3 times the speed of sound, 2,000 miles per hour, at altitudes of 70,000 feet. The major objectives of the XB-70 flight research program were to study the airplane's stability and handling characteristics, evaluate its response to atmospheric turbulence, and assess propulsion system performance. The wingtips could be lowered in flight to allow the aircraft to cruise at higher speeds more efficiently. At these higher speeds, water vapor condensed at the forward control surfaces. The vapor can be seen streaming from the aircraft. A program to develop the piloting techniques that were used during the final phase of the manned lunar landing was started at the Flight Research Center in 1964. This program used a free-flying simulator called the Lunar Landing Research Vehicle, or LLRV. To compensate for the gravitational and atmospheric differences between the Earth and the Moon, the LLRV was equipped with a gimbaled jet engine that produced enough thrust to counterbalance 5/6 of its weight, thereby simulating 1/6 gravity of the Moon. Small rocket motors were used by the pilot to control horizontal and vertical movement in a simulated approach to the surface of the Moon. One of the research craft recently tested at the Flight Research Center was the M2 lifting body. The M2 was towed to altitude by a C-47 aircraft. Lifting bodies are wingless vehicles that obtain aerodynamic lift for flight from the shape of their bodies. Vehicles like these are being tested to obtain basic flight test data to aid in the development of future space shuttlecraft that will be used to supply men and materials to orbiting space stations. 3 minutes after launch, the M2 began its final landing approach. Total flight time for a normal glide flight was almost 4 minutes. The HL-10 was the second manned research craft of the wingless lifting body class of re-entry vehicles studied by NASA. It was flight tested to provide technology for the design of future spacecraft that are maneuvered in flight to normal landings at selected landing sites. During the final approach, the HL-10 pilot pushed over to increase the horizontal speed before performing the flare maneuver to cushion the landing. The HL-10 landing speed was about 230 miles per hour, and rollout was approximately 1.5 miles. The X-24A was another of the 3 lifting body shapes which have been flown at the Flight Research Center. First flown on April 17, 1969, the craft made 28 flights. Top speed reached by the X-24A was 1,000 miles per hour, and the highest altitude was 71,000 feet. A new airfoil shape called the supercritical wing is being flight tested aboard an extensively modified F-8 jet aircraft. Almost the direct opposite of conventional airfoil shapes, the supercritical wing has a flattened top surface which delays shock wave formation and increases the total wing efficiency. An advanced flight control system called the Digital Fly-by-Wire System has been installed by the Flight Research Center in a modified F-8 jet aircraft. The heart of the control system is a digital computer and an inertial measuring unit that were developed for the flight control system of the Apollo lunar module. Use of this kind of control system could make air travel of the future smoother and safer by reducing aircraft vibrations caused by turbulent air through automatic response from the computer to the aircraft controls. The National Aeronautics and Space Administration has assumed operational control of 2 YF-12 aircraft being flown in a joint Air Force-NASA research program. The basic purpose of the YF-12 flight research program is to obtain information from sustained cruise flight at Mach 3, approximately 2,000 miles per hour, at altitudes near 75,000 feet. Data obtained from the program will be used to further the development and operation of supersonic aircraft, both commercial and military, and the proposed space shuttle. Major areas of interest in the NASA portion of the program are structural and performance research. Other research regions include stability and control, aerodynamics, the physiological and biomedical aspects of sustained high-speed cruise, and the physics of the upper atmosphere. Future aircraft design will depend on the work we do here today at the NASA Flight Research Center. And so, after 25 years of basic research into all the facets of manned flight, the NASA Flight Research Center is ready for the challenge of tomorrow, looking forward to new horizons to come.